rewatch us going through the notes tonight. If there's some stuff that I went over that you thought you got down, but then you get to the homework and you're like, I maybe don't have this down. I am recording going through the notes, so you can always jump back onto the Google Classroom and check out the video under the Zoom class videos section. For today, October 14th, we're going to be talking about density. And so the video of me going through the notes with y'all today will be right here in the density section. But if you want to see the actual notes themselves, we move all the way down to the bottom of the page, getting through week 7 now, which is still crazy to me. So our October 14th Wednesday notes are on density. So this is kind of continuing the idea of scientific measurements that we talked about last week with like the grams and the milliliters and the centimeters cubed and all that fun stuff. And so today we're going to be talking about a different type of measurement of a substance of matter, which is its density. So density might be something that you've like heard of before, kind of, sort of, in a roundabout way. So you may think, oh, if like something or somebody is really dense, that means that they're really heavy, which partially is true, but that doesn't really tell us the full story of what exactly density is. Density is not just weight. So remember last Wednesday, we talked about measuring things in kilograms and grams and milligrams, and that is something's weight or its mass. Density is a little bit different than that. Density doesn't just refer to weight. It instead is a measurement of how compact a material is, how much material is stuffed into a certain area, a certain volume. So it's one way of measuring how close our atoms or molecules are to each other. So when we talked about bonding from a couple weeks ago, we had those ionic bonds and those covalent bonds, and they cause the atoms to kind of stick to each other. In some substances and in some states, like solids versus liquids, the atoms are closer together, and in some of them, the atoms are farther apart. And density is a measurement of how compact, how close together we can cram a whole bunch of these different atoms or molecules. So it's more than just heaviness, right? It also includes how much space an object takes up. So if you lift it up like a giant box full of packing peanuts and a little box full of, like, I don't know, computer parts or metal or some kind, the boxes might weigh the same, right? The big box, even though it's full of really light stuff, like those little foam plastic peanuts, it's a big box with a lot of those in it, so it feels kind of hefty. And then a little box with a whole bunch of junk, metal, computer parts, and plastic parts is also going to be pretty heavy. But even though their weight, their heaviness might be the same, the small box with the metal computer parts is more dense than the big box because it's the same weight, but in a smaller area. So it's more compact weight compared to the large box. All matter, all substances in the universe have density. Not just things that you might think like liquids and solids, but gases as well can also contain density. We can also measure the density of gases. So it's kind of a visual component of everything. If we have a less compact, which would also be a less dense material, that means that the atoms in that material are a little bit more spaced out. There's a little bit more space between the different atoms and molecules. Whereas in a more compact or a more dense material, the atoms are going to be really squished tight and close together. So these atoms are really close to each other. There's a lot of overlap that you can see. They're all kind of lined up in these really tight rows. These guys up here are all just kind of loosey-goosey. They're all just sort of floating around each other, not really condensed or compacted together. So one way that I like to think of it is with like a trash can, right? During the week, you're just kind of throwing stuff into the trash can, and maybe like a couple days in, it starts to get full. Do you just immediately go and take out the trash as soon as your trash is full? No, of course not. You reach in there with your foot or your hand or a paper towel or something, and you squish it down into the bottom of the trash can. When you do that, you're making that trash more compact. You're increasing the density of your trash because you remove a lot of the extra air and space between all the different trash. So now you can add more trash in there. You can add more weight to your trash can, which is already a set size, right? So less compact, things are spaced out. There's a lot of space in between our different substances, like in a partially full trash can. More compact, if you squish all that trash down, you remove a lot of that space. You get rid of a lot of the area. And so you make it more compact. You get all of that stuff closer together. So that's what density is measuring, is how compact, how dense is this material? How much weight does it take up if it's in a certain space, a certain area? Any questions so far on what density is or kind of what it represents? All righty, doesn't sound like anybody is getting stuck on anything so far. So we will keep moving along to probably the most important couple slides of this lecture. So if you're kind of spacing out a little bit before, focus back in because we're about to get real important. So you may have heard me mention a whole bunch of stuff regarding density just now. How much matter that you have or its weight and how much space that it takes up. So density is the ratio, is the comparison of mass or weight to volume or space. So if the volume of our subject, of our matter, stays the same, but the weight increases, it gets heavier, that's when our density increases. Our density goes up. So this would be like if you had your trash can that was like partially full of trash, and then you squished it all down and added a whole bunch more trash on top. Your volume would stay the same because your plastic trash bin isn't changing. It's not getting any bigger or smaller. But you increased the mass of the trash that's in there. So you added more trash, you added more weight. So you increased the density of the trash. You added more weight into the same area, the same can, so the density went up. You have a more dense trash can now than you did earlier. On the flip side, if the mass stays the same, but the volume increases, now your density goes down. So this would be like if you had your little mini trash can in your bathroom that was starting to get a little full, and then you took it and you dumped it into your empty big trash can in your kitchen, the density of your trash went down. Because before, there was a certain amount of trash in a small space. we moved that trash. So it's the exact same trash. It has the same mass, but we moved it into a much bigger area, a much bigger space with more volume. So our density of our trash went down. We have less compact, less kind of filled in trash. So it's all about mass and volume. These two things together tell us the density of an object. So if we put this together and actually want to measure or calculate what the density of a specific object is, then we can do a very simple math equation in order to figure that out. So the density of an object, this D over here means density, is equal to mass divided by volume. D equals mass divided by volume. So our mass is usually expressed in units of grams. So we talked about grams last time. That's like our base metric unit for weight. And volume we usually express in either centimeters cubed or milliliters. So most expressions of density are in grams per centimeter cubed. How much weight does this object have if we have a single cubic centimeter of volume? That's usually what density represents. So if you have some sort of unknown object, but you can measure its mass, its weight, and you can calculate its volume, then you will be able to know what the density of that object is. So this is what you're going to be doing a lot for the assignments for today and tomorrow, is calculating the density of different unknown objects. So our mass in grams divided by our volume in centimeters cubed or milliliters gives us the density of a material, of a certain either atom or molecule or compound or mixture, whatever it is. If we know its mass and we know its volume, we can calculate the density. So based on our simple little equation, density equals mass divided by volume, what happens if we know what the density is and we know, say, what the mass is? Can we use that to find the volume? The answer is yes. Our volume is equal to the mass divided by the density. So instead of doing mass divided by volume in order to find our density, if we know the mass and we know the density of our object, we can do mass divided by density, and that'll give us our volume. Same exact thing, switched around a little bit more for if we know the density of our object and we know its volume, but for whatever reason we're not able to measure its mass, then we can do another simple little equation, density times volume, and that will give us the mass of the object. So no matter what value you're looking for, as long as you have the other two values, you can figure out your one unknown. So what this little triangle over here on the right-hand side is showing is the relationship between the three different measurements: density, mass, and volume. So it shows us that if we know, the way that you read it is that if we know the mass and we know the volume, then according to this triangle, we can do mass divided by volume, and that'll give us our density, just like our density equation over here. If we know our mass and we know our density, then we can do mass divided by density, and that will give us our volume. So mass over density gives us volume. And then finally, if we know what our density is and we know what our volume is, then we can do density times volume, and that will tell us our mass, our M. So density times volume will tell us what the mass of an object is. So on your assignments for today and tomorrow, it'll be a series of questions where each question will give you 2 of the variables, and you have to do some simple math in order to solve for the third one. A lot of the questions will be asking about density. So it'll tell you this material has a mass of 10 grams and a volume of 5 centimeters cubed. What is the density? And so you do, okay, well, 10 grams divided by 5 gives us a density of 2. But not all of them ask for density. Some of them might say, okay, well, if our mass is 10 and our density is 2, what is our volume? And so you just have to say, well, I know volume equals mass divided by density. So 10 divided by 2 gives us a volume of 5. And then finally, it could also tell us the density and the volume and say, okay, what is the mass of this object if the density is 2 and the volume is 5? And it'll be up to you to figure out, well, if I know density and volume, then I have to do density times volume, and that'll tell me that the mass is 10. So that's how you use these density equations. If you have 2 of the 3 numbers, 2 of the 3 variables, then you can do a simple math equation in order to figure out that one unknown. So this is probably the most important aspect of density that we're talking about tonight, because it does directly relate to your next 2 assignments. So does anybody have any questions about the density equations? Anything that I went over that you're still not really sure about or you didn't quite get the first time? Any questions, issues, concerns with our density equals mass divided by volume equation? All righty, well, I'm not hearing anything on the speakers and I'm not seeing anything pop up in chat. So hopefully that means that this all is making sense to you so far. Again, I am recording this, so if you want to go back and watch me explain it again at a later date, you're always welcome to. Or if it sounds great right now, but 4 hours from now, it all sounds, you can't make heads or tails of it and it all looks like gibberish, shoot me a text or an email or leave a comment on the Google Classroom, and I'll be more than happy to go over it with you again a little bit more one-on-one. All right. The last couple slides I'm going to go through pretty quickly because they just are kind of demonstrating some of the different principles of how density works in different situations. So I mentioned earlier that solids, liquids, and gases have density. So gases you normally don't think of as being very dense, right? Because they're around you all the time. You can't really feel them. And the air, there's not like a weight that's pressing down on you, at least to your observations. But gases do still have density, right? I don't know if you've ever walked outside when it's like 93 degrees and 100% humidity, and you can like feel that stickiness in the air. That's part of the density of that water molecules in the air, making it so humid and sticky. So one of the interesting things about gases is that because gases, if you remember way back when we first started talking about the different types of matter, solids, liquids, and gases, we said that gases can expand and contract in order to fill up their area. They don't have like a set particular volume. So as the kinetic energy of gases goes up, hold on, let me switch to easier to see color. As the kinetic energy of the gases goes up, which if you recall, kinetic energy is related to temperature. So the faster that the gases move, the more and the hotter that they get, the more space that they take up. So the faster those particles are, the more that they spread out. So what this means is that if you remember back to our density equation, density equals mass divided by volume. When gases get bigger, their volume goes up. And when the volume goes up, that means that our density is smaller, right? If you remember back to your fractions days, when the number on the bottom of the fraction gets big, that causes the overall fraction to be even smaller, right? 1/2 is a lot bigger than 1/8, right? So when volume goes up, density goes down. So gases heat up, the volume gets bigger, they take up more space, the density goes down, which is why warm air rises and cold air falls. So cold air is more dense than warm air. That's why the top floor of your house, if you're living in like a second story house or apartment, tends to be warmer than the bottom floor because the warm air in your house will tend to rise while the cold air goes down. Exact same principle for a hot air balloon. So a hot air balloon, we have our little basket, and then there's that little thing with all of the fire coming out of it. And then there's the big balloon that goes around it. The reason why hot air balloons are able to lift off the ground and float through the air is because the hot air inside the balloon is trying to go up above the cold air that is around the balloon. So the hot air is less dense, which means that it wants to rise above the cold, more dense air. So that's how gases relate to each other in terms of their density. Warmer gases tend to rise because they have a lower density. Cooler gases tend to fall because they have a greater density. Same thing happens to liquids. Liquids come in all sorts of different densities, and the more dense the liquid, the more likely it is to fall to the bottom of a certain mixture. So like in this glass beaker over here, We have this extremely dense dark material here down at the bottom. It looks like probably some sort of motor oil. And then we have less dense water above it, and then even less dense oil of some kind on top of the water. So these liquids are separating apart from each other due to their different densities. The temperature effect also happens in water and liquids as well. Cold water tends to sink to the bottom of areas, and warm water tends to rise to the top. All right, so a quick, really interesting example. Mercury is a metal with a fairly high density, 13,600 kilograms per meters cubed. Lead is also a metal with a fairly high density, 11,340. But one of the really cool things about mercury is that it is a metal that is liquid at room temperature. So it is this really cool silvery liquid that is pure metal, pure mercury. So if we have like a situation down here where we have a glass full of mercury with this density of 13,600, and we place a hunk of lead into it. So we drop some lead into the mercury with this density of 11,340. What do you think is going to happen to this block of lead? Is it going to sink or float on our mercury?
Float. Float.
Float. That is 100% correct. So even though lead is a very dense and very heavy metal, mercury, even as a liquid, is even more dense than the lead. So this is like an old school pool ball that has a core of lead on the inside. And so it floats on this big container of liquid mercury down here because it is less dense. So the thing that determines whether or not this lead floats is dependent on the substance below it. Water is much less dense than these big metals, so the lead would sink in water, but due to the liquid mercury being more dense, the lead floats on it instead. Good call on that one. So solids, as you might expect, normally are more dense than liquids and gases. The density of solids can vary widely between if it's a metal or a non-metal or a compound of some kind or some sort of alloy. But in general, the solid version of a substance will be more dense than the liquid version. So normally, as things freeze and become solids, those atoms get very compacted and close together, which is, again, what gives us our higher density. They're more compact. One of the really interesting exceptions to this rule, however, which is a really important facet for life on Earth, is ice versus water. So when you have your big cup of soda or water or whatever it is, and you drop in the ice cubes, they don't sink down to the bottom, right? They float on top. Even though normally we would think that solid water, aka ice, would be more dense than the liquid water. But water, H2O, flips the script, and solid water actually floats on liquid water. It has a slightly lower density when it's ice versus when it's water. This is extremely important for things like lakes up in the north, where they freeze over in the wintertime. If solid ice sank to the bottom of the lake, then in the winter, the top part of the ice where it hits the air and is coldest would freeze over and sink, and that ice would kill all of the animals and plants that live down underneath the surface of the water, which would be bad. We wouldn't have any of the diverse plants and animals that live in our lake ecosystems if they always got killed by falling ice. Instead, luckily for us, ice floats on water. It has to do with the complex way that the H2O molecules interact with each other when they are frozen that we're not really going to get into in this class. That's like a pre-AP or AP chemistry class. But just know that it's due to density. So ice has a slightly lower density than water, and that allows it to float. There are a couple different things that can affect the density of a substance that I'm going to run through just really quick. So temperature, we already talked about. Hot substances tend to be less dense than cooler substances, especially things like gases and liquids. Pressure, if you increase the pressure of a certain area in a certain substance, that can change its density. If things are dissolved in a substance, that can also affect density. So if you've ever been swimming in the ocean versus swimming in a lake, you float a little bit better in the ocean than the lake. That's because the ocean is full of salt water, which, as you might suspect, has a whole bunch of salt dissolved in it. And because it has all of this extra salt dissolved in it, it's a little bit easier for people to float on the ocean because there's a little bit higher density. If you go to the Red Sea in, I believe it's in Eastern Europe. Egypt, thank you. It has an extremely high salt concentration in it, way more than the normal lake or ocean. And so people can like bob up and down like corks on the surface of the sea because of the extremely dense water and dissolved substances underneath them. So the
Great Salt Lake.
Yeah, Salt Lake is also similar to that. The more salt, the more substances you have dissolved in your liquid, the more dense it will be because you have more mass in that certain area, and the easier it is for things to float on the top. So speaking of things floating, if you want to determine, we already talked about with that mercury versus lead example, that less dense things tend to float on top of more dense things. And so if you're thinking about water, just normal, standard, purified water, it has a density of exactly 1.0 grams per milliliter, or grams per cubic centimeter, is the density of water. So if you want to determine if something will float or sink if you chuck it into the pond, if you know its density, it can tell you if it'll float or sink on your water. So obviously air is extremely low density. Gases will almost always have a much lower density than solids or liquids. So air, obviously, that's why the bubbles in your Coke will rise to the top, because they're little dissolved carbon dioxide bubbles that want to float up and escape from the more dense water or more dense soda. Wood, even though it is a solid, it's not relatively dense due to all of the cellular structures and spaces between the wood cells. So it has a little bit lower density of water. So it would float on water. Ice, we already mentioned, is just underneath the density of water. So water is at exactly 1.0. Ice is just under that at 0.93. So ice would float. Obviously, things like heavy metals such as aluminum or lead or gold have a somewhat high density to a very high density. So they would all sink in water. If you crushed up your Coke can, or you took a chunk of lead or gold and tossed it into the water, it'll make a big splash and sink right to the bottom because of that higher density. Certain compounds like ethanol, which is the alcohol that we use to drink, or methanol, which is an alcohol that's used in certain types of fuels, is also slightly less dense than water. So that's why if people are making like those flaming shots that you can get at bars sometimes, they'll put a really high alcohol drink right on the top of that, because that ethanol will float on the top of whatever sort of mixed drink you have underneath it. And that's what they light on fire when they do those burning shots, is the ethanol that's sitting right at the very top layer, floating on the water due to its low density. So density tells us about the compactness of a material, how much weight is in a certain volume of it. We can determine density by doing the mass divided by the volume in order to figure out how dense is this material. Different factors like temperature and salinity can affect how dense a substance is. And less dense substances will float and separate out on top of more dense substances, whether or not they're less dense due to temperature or due to being different materials. If you compare the densities of two objects, the less dense one will rise to the top and the more dense one will sink to the bottom if you combine them.
Okay, so what about oil?
Oil is, I don't think it's on this chart, but oil is, for the most part, there are different oils, but in general, it is, I think it's less dense than water. I'd have to look it up for sure, but that's a lot of times what'll create like oil slicks, like when you have a big spill of oil in, like the one that happened in the Gulf of Mexico with the Deepwater Horizon vent that got opened. All that oil rose to the top of the water and was kind of floating around on the surface due to the differences in density between oil and specifically salt water, which is obviously what's out in the ocean. So salt water would have a little bit higher density than normal, like purified water. All right, good question. Any other density related questions? Anything that I went over that you didn't quite get the first time or want another brief look through?
I did. When you changed it from the lead, was it lead that you say it can be liquid?
Mm-hmm.
And you said that when it turns into a liquid, I can't remember if you said it float or if it got heavy.
With like the lead and the mercury?
Yes.
So mercury is room temperature or is a liquid at room temperature. It's one of the few metals that does that. Lead is not, it's normally a solid. So normally when you're comparing solids and liquids, you would expect that the solid would sink in the liquid. It's normally more dense when it's solid. However, because mercury has such a high density compared to lead, even though the mercury is liquid and the lead is solid, the lead still floats on the mercury. The density of mercury is higher as a liquid than the density of lead as a solid, which is why the lead will float on top of the mercury. Did that help answer your question a little bit, Monica?
Yeah, I think I had it the other way around. So it's mercury that can turn into liquid.
Mm-hmm. Yeah.
Okay, I had it the other way around.
Gotcha. So yeah, it's mercury that's liquid. I mean, lead can also turn into liquid, but you got to get it really, 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 really hot to do that, like hundreds or thousands of degrees Fahrenheit. Mercury will turn into liquid at like 75, 78 degrees Fahrenheit, which makes it kind of cool for a metal. Any other density related questions? Anything you want me to go back and touch on really quick? All right, sweet. So we got a couple more minutes. So I just wanted to really quickly show you guys the assignments for today and tomorrow. So the one that got posted today is kind of the first set of density related questions where, like I mentioned, make sure you guys are, yeah, okay. So you're going to be given a certain set of questions. There's an example one up at the top if you want to remember the density equation, mass divided by volume. So the first couple equations just ask you to determine the density of certain objects. So it gives you the mass and the volume of a loaf of bread, for example, or a block of wood. The next couple switch it up a little bit. So number 3 wants you to figure out the mass of some unknown substance, and it gives you the density and gives you the volume. And then number 4 switches it up again a little bit. It wants to know the volume of a certain ball, and it gives you the mass and the density. So depending on what sort of information that you get, you should be able to use one of our density equations. So if you ever want to go back and look at it, it's slide 6 on our notes that we went over today. And so if they're also sometimes given to you directly in the question itself. So that is the assignment that got posted today. And then the one that will be posted tomorrow is essentially more of the same to give you guys a little bit more practice with this density stuff. So a lot of similar setups. It gives you volume and mass, and you have to figure out density. Or maybe it'll give you density and mass, and you have to figure out volume, et cetera, et cetera. The one question that changes it up a little bit is number 5 down here, where it tells you what the density of 2 different metals, silver and aluminum, are. And then it gives you a dimensions of a cube. So you can figure out the volume by multiplying the height, width, and length. So you determine the volume, it gives you the mass. And so based on your volume and your mass, you have to determine, is this unknown substance silver if you get one density, or is it aluminum if you get the other density? So the same equations, the same kind of practice as you've been doing, just presented in a little bit different way. All right, any final density related questions? Anything that you're still a little bit not sure or have questions about? Nope. All righty. Well, as always, if you do find yourself struggling a little bit over the next couple days, you can always reach out, shoot me a text, send me an email, leave a message on Google Classroom, and I will get back to you as soon as I can. Couple things, couple final announcements before we log off. One, the next week is the last week of classes, which I know, crazy. So when we reach the end of the semester, next Thursday, so the 22nd, that is going to be the last day that you have to turn in any of the assignments that are still due at that point. So if you have any work that you haven't completed yet, or it's work from a couple weeks ago that you just never got around to. The end of the day, next Thursday, the 22nd, is the last day that you'll be able to turn that in and get graded on it. Our final.
Okay, so since you mentioned that, I just saw I went on Skyward just to see, there's just placeholders for the last 3 assignments. So by the 21st, that's when the grades will be updated.
Yeah, so I'll
Okay.
make sure to be keeping updating everybody's grades over the next few days. I'm also going to try to put together a list to send out to people if you are still missing assignments by either late this week or early next week, just so that you can kind of double check and see if there's anything that you're missing. You can also always go through Google Classroom and see if there's anything that you haven't turned in yet. I promise that anything that you have turned in and has a grade on it will be put into the grade book by the time that classes finish up.
Mr. Stanley.
Yes, ma'am.
You know the how you said that it'll say turned in if you do it. Some of them I was doing with attachment, so then I would go back and press the turn in button, but it would be blank. So I'm not sure which ones I missed on turning them in for reals, because I tried to go by that list where you said to go to our work.
So if there are attachments on it, I should be able to see that and give that a grade, even if you didn't necessarily hit the turn in button. But if I don't, so I'm going to be going back and checking over the next day or so. And if there's something that I haven't received from you yet, or I don't have anything to grade from you, then I'll reach out and let you know that either I, for whatever reason, never got it, or you still have to complete that assignment.
Thank you.
Yep, no problem. And then last thing I wanted to say before we log off that is not specifically school related, but early voting opened in Texas yesterday. So if you are registered to vote in the Austin area, please, you don't have to wait until November 3rd. You can vote any day of the week, including Saturdays and Sundays from now until October 30th at certain polling locations around Austin, Cedar Park, Round Rock, Pflugerville, different areas in Austin. So you can go online in order to look up where the early voting places are. And all elections are important, but this election is especially important. So I just want to make you guys aware that if you are registered to vote in Travis County or Williamson County or one of the other nearby Austin related counties, then early voting is now open and you can vote at certain polling places anytime, or not anytime, but any day between now and October 30th, including Saturdays and Sundays. So if Tuesday, November 3rd is not a good day for you to be able to get off a couple hours out of work and go vote, then please think about doing some early voting, and that way you can do it on a schedule that is better for you.